In this lecture, we will outline some characteristics of data samples and also delineate some principles before looking into a few more methods of likelihood estimation. So, the first thing we want to define are the criteria called sufficiency. So, a statistic is denoted by vector t, which is a function of the data samples x1 up to xn. This is basically t1 of x1 all the way up to some capital M. Capital M denotes the number of components in T. So this statistic is sufficient for a parameter set theta if the distribution of a sample comprising of x1, x2 up to xn given t does not depend on theta. So basically f of x1 up to xn so the distribution g of t given theta contains all the information which is relevant for the parameter estimation. So this means that for the estimation process, we can replace the sample by the sufficient statistic. In this way, we may reduce the amount of data considerably. The relevance of sufficiency is expressed in a different way, in the so-called sufficiency principle. So if two different sets of observations have the same values of a sufficient statistic, then the inference about the unknown parameter should be the same. Of special interest is what is known as minimal sufficient statistic. It consists of a minimal number of components, so ideally only one element per parameter. So if we consider the case of a one-dimensional sufficient statistic, and a single parameter theta, then the likelihood function can be written as it is easy to realize that the second factor L2, which is independent of theta, has no bearing on the likelihood ratios of different values of theta. So we obtain a data reduction of n to 1. This means that all samples of size n, which have the same value of the statistic, lead to the same likelihood function and thus to the same maximum likelihood estimation and the same likelihood ratio interval. Now, if in the general situation with p parameters or minimal sufficient statistic of p components exist, the data reduction is n to p, and the maximum likelihood estimate for the p parameters will be a unique function of t, and therefore itself is a sufficient statistic. Let's consider an example. So we look at the sufficient statistic and expected value of a normal distribution. So let x1 up to xn are normally distributed. Observations with sigma. The parameter of interest is the expected value of the distribution. The likelihood function is L for mu given x1 xn is some constant, is nothing but 1 by 2 pi sigma square of n and then the product over the exponentials. Of course, we can turn the product over exponentials into exponential over a sum. The exponent can be, the argument of the exponent can be rewritten like this. Then the likelihood will factorize as Only the first factor depends on mu. As a consequence of this, the experimental quantity x bar contains the full information of mu and thus is a one-dimensional sufficient statistic. And setting the derivative of the first factor equal to 0, that basically gives the maximum likelihood estimate of mu at equals x bar. In the considered example, the likelihood function is fixed up to an irrelevant multiplicative factor if we consider the sample size as a constant. In case the sample size, capital N, is also a random variable, then N is a part of the sufficient statistic. Now let's define something known as the conditionality principle. The conditionality principle states that if an experiment concerning the inference about a parameter theta is chosen from collection of possible random experiments, independently of theta, then any experiment not chosen is irrelevant to the inference. Next, we'll discuss a principle which concerns the foundations of statistical inference and plays a central role in Bayesian statistics. So we discussed the so-called likelihood principle. The likelihood principle states that given a probability density function containing an unknown parameter of interest, and an observation all the information relevant for the estimation of the parameter is contained in the likelihood function. Furthermore, two likelihood functions which are proportional to each other contain the same information about theta. The general form of the PDF is considered as irrelevant. The PDF at variate values which have not been observed has no bearing for the parameter inference. So as an example, let's say we have a bag of bias dice. Of two types, A and B. And they produce the different numbers with different probabilities. Let's say the result of an experiment where one of the dice is selected randomly is 3. And then we are asked to bet for A or B. Now, we are unable to draw a conclusion from the observed result because both dice produce this number with the same probability. The likelihood ratio is equal to 1. So the likelihood principle tells us that what intuitively is clear, that for a decision, the additional information, that is, the probabilities of the two dice to yield values different from 3, are irrelevant. So we only need to know what the probabilities are for them to yield 3. The likelihood principle follows inevitably from the sufficiency principle and the conditioning principle. And it goes all the way back to Fisher, but has been reformulated and derived several times. Now, if we think of the frequentist statistics, then one important aspect of point estimation is the evaluation of the bias of an estimator. So, bias, which we'll denote by small b, of an estimate theta, is the deviation of its expectation from the true value of the parameter. So, let's say, as an example, we look into the bias of the estimate of a decay parameter. So we estimate the decay parameter gamma from 5 observed decays. Of an unstable particle. The maximum likelihood estimate is the inverse of the average of the individual decay times. This was derived in a previous example. And the mean values T bar follows a gamma distribution. Therefore, the expectation value of the maximum likelihood estimate is Notice that one power of t bar is cancelled by gamma hat, because gamma hat is 1 by t bar. So when a large number of similar experiments with 5 observed events, the maximum likelihood estimate of the decay time is determined, then the arithmetic mean differs from the true value by 25%. And the bias is gamma by 4. If the same computation had been done for a single decay, the bias would have come out to be infinite. With increasing number of observations, the bias decreases when we say that the maximum likelihood estimate is a consistent estimator. The likelihood estimates have the desirable property that they are invariant against parameter transformations. So for instance, estimates for the rate and mean life. So gamma and tau bar, they obey the same relations as the true values. That is, once the true values obey the relation gamma equals 1 by tau, the estimates also do the same. But the corresponding relation is not valid for bias corrected quantities. In general, the bias is not invariant against parameter transformations, and thus its correction is problematic. The requirement of an unbiased estimate, on the other hand, is in conflict with parameterization invariance. Now we'll shift our discussion away to a few more methods of parameter inference. We'll start by discussing what is known as the moments method. So the moments of a distribution, which depends on a parameter theta, also depend on theta. So mu n theta, which is given as the empirical moments for example, the sample mean or the mean of squares, which we can extract trivially for a sample, are estimators of the moments of the distribution. From the inverse function, we obtain a consistent estimate of the parameter. It is clear that any function u of x for which the expected value and variance exist, and whose expectation is an invertible function of theta, can be used instead of x to the power n. Therefore, the method is somewhat more general than suggested by its name. If the distribution has several parameters to be estimated, we must use several moments or expected values, approximate them by empirical averages, and solve the resulting system of, in general, nonlinear equations for the unknown parameters. The estimators derived from the lower moments are usually more precise than those computed from the higher ones. Parameter estimation from the moments is usually inferior to that of the maximum likelihood method. Only if the moments used form a sufficient statistic, the two approaches produce the same result. Next, let's look at the least square method. So frequently occurring problem is that measured points and error margins are given through which we want to fit a curve. The curve so y equals this parameterization. Let's say this is measured at a finite number of positions giving yi for each of the xi. The standard solution of this so-called regression problem is provided by the least square method, which fixes the parameters of a given function by minimizing the sum of the normalized square deviations of the function from the measured points. So, given n measured points, xi and yi along with some errors associated with them, and a function known up to some free parameter as theta. The latter, the functions are determined such that chi square takes its minimal value. The least square method goes back to the time of Gauss, and historically it has been successful for astronomical problems and is still the best method. We have to adjust parameters of a curve to measured points if only the variance of the error distribution is known. It is closely related to the likelihood method when the errors are normally distributed. In such a case, we can write down the PDF of the measurements as being proportional to the log likelihood actually it should just be a sum over I. And this is nothing but minus half of chi square. So once again, minimizing chi square is equivalent to maximizing the likelihood if the errors are normally distributed, a condition which frequently is at least approximately satisfied. So we can generalize this to the case of correlated errors. So in which case chi-square is given by a matrix multiplication V, which is known as the weight matrix, is the inverse of the covariance matrix. And maximizing likelihood is again equivalent to minimizing chi-square if the errors are normally distributed. The sum chi-square is not invariant against a non-linear variable transformation. We go from y to y prime. Now, as an example, let's look at fit of a straight line. So we fit the parameters of a straight line. To a sample of points with uncertainties delta I of the ordinates, it is the y coordinates. So chi-square in this case is again defined as yi minus axi minus b and we minimize it by first computing the partial derivatives. So set the derivatives equal to 0 and we introduce the following abbreviations. So x bar is the sum over xi by delta I square, sum over 1 by delta I square. Similarly, we have yi also x bar square and xy bar. Of course, in the case where all certainties are equal, all uncertainties are equal, that is, If delta I equals delta, then these expressions simplify further and we have this. So basically obtain based on the minimization. Which basically allows us to write this problem is simplified when we put the origin of the abscissa at the center of gravity. So if we instead have x prime equals x minus x bar, then we get the estimate a prime hat as similarly b prime hat is just y bar. And now the equation of the straight line becomes and this also gives us an additional advantage that the errors of the estimated parameters are no longer correlated. Now, if the prediction depends only linearly on the parameters, we can compute the parameters which minimize chi-square analytically. So theta is a p-dimensional parameter vector. A is a given n-dimensional vector. Yt is the n-dimensional vector of predictions. And capital T, which is also known as the design matrix, is a rectangular matrix of given elements with p columns and n rows. The straight line fit that we discussed in the previous example is a special case of this, with yt being theta 1x plus theta 2 and a equals 0. Now, you want to find a minimum of the chi-square given by, it's expressed as a matrix product, so once again we use the weight matrix or the inverse of the covariance matrix. So in our case it is just a diagonal n cross n matrix with elements one by delta I square. To simplify the notation, we transform the observations as write y prime as y minus a. This allows us to write the chi-square is simply y prime minus t theta transpose times v times y prime minus t theta. Now we take the derivative of this chi-square with respect to the parameters theta and set the derivatives equal to 0. Basically equated to the 0 vector. And from these so-called normal equations, we get the estimate for the p parameters. As now this T transpose V times T is a symmetric P cross P matrix which has a unique inverse, and this turns out to be the error matrix of theta. And this was just a glimpse into what's known as linear regression. Now, linear regression provides an optimal solution only for normally distributed errors. If the distribution of errors is not known up to their variance, it is, according to the Gauss-Markov theorem, optimal in the following restricted sense. If the error distribution is mean value 0, the estimator is unbiased. And among all other unbiased estimators, which are linear in the observations, its estimator has minimal variance. In fact, the result then coincides with that of a likelihood fit if normally distributed errors are assumed. But linear problems are rare. When the prediction is a non-linear function of the parameters, the problem can be linearized by a Taylor expansion as a first rough approximation. By iteration, the precision can be improved.